So in today's lecture we are going to see about a steady state error. So what is a steady state error? A steady state error is the value of the error signal. Value of the error signal E of t when time t tends to infinity. Right? So how this steady state error occurs in control system? So actually this steady state error is a measure of system accuracy. So based on this value of the steady state error, we will come to a conclusion about the system accuracy, right? So these errors arise from the nature of inputs because you will be applying different inputs to any system, and therefore the nature of the system input what you are applying, that will decide the amount of steady state error. So when t tends to infinity, or when the system is in its stable state, how much will be the error? Because of the non-linearities present with the input signal or the non-linearity of the system components, so there will be some errors when the system reaches its steady state value. So that is what the steady state error. So in this lecture we are going to see the different types of steady state error and how to calculate the steady state error in different cases. So for the analysis purposes we will be using the basic or standard signal, standard input signal to find the steady state error. The standard input signals like step signal, a ramp signal, or a parabolic signal. So by applying these different types of input signal, we will be analyzing or will be finding the steady state error. So you just consider a system like this. So here the R of s is the input and E of s represents your error signal, right? G of s is nothing but the open loop transfer function that already you know, and H of s is the feedback transfer function, and C of s represents your final output, right? So here R of s is nothing but your input signal, right? And E of s is your error signal. So once you have calculated the error signal E of s, so from that we can find the value of E of t just by taking the inverse Laplace transform of this E of s, and we can obtain the value of this error signal E of t when t tends to infinity, that is nothing but your steady state error. So from this block diagram, so we can write this E of s as E of s equal to, or the error signal E of s is nothing but R of s minus C of s into H of s. You see the feedback signal is nothing but a C of s into H of s. So it is subtracted at this point. Therefore this E of s is R of s minus this C of s into H of s. Or we can write C of s is nothing but your error signal E of s into H of s. This is what your C of s. Your C of s is nothing but a error signal into your G of s. That is what written here. So now if you substitute this value of this C of s, so you can number this equation number 1. If you substitute this value of the C of s in this equation, you will get E of s is equal to R of s minus E of s into H of s, E of s into G of s. So this one is G of s, right? E of s into G of s into H of s. Just I have substituted this value because this E of s is E of s into G of s, right? E of s into G of s. Therefore you will be getting E of s equal to R of s minus E of s into G of s into H of s. Or we can write this as E of s plus, you can bring this term here, E of s into G of s into H of s is equal to your R of s, the input signal. Understood? So now from this equation we can write what is E of s. So that we can write E of s is equal to R of s divided by 1 plus g of s into h of s, right? So once you take this e of s common, you will get so, or you can write one more step here. So e of s into 1 plus g of s into h of s is equal to r of s, and hence therefore we can write this as e of s equal to r of s divided by 1 plus g of s into h of s. So now your error signal is nothing but e of t. Therefore once you take Laplace inverse of your e of t, you will get a Laplace inverse of your e of s, you will get a e of t. So that is nothing but the Laplace inverse of r of s divided by 1 plus g of s into h of s. Now the steady state error, we can represent the steady state error as e suffix s suffix s, ess. So this represents your steady state error. So now this steady state error is nothing but the value of e of t, or the error signal when time t tends to infinity. Or we can write this e of ess is equal to limit t tends to infinity e of t. Understood? So after calculating this e of t, we can find this ess, or the steady state error, by substituting t equal to infinity in that equation. Or you can use an alternate method, that is nothing but your final value theorem of Laplace transform. You can apply the final value theorem of your Laplace transform to find this steady state error. Right? So what is the final value theorem? So if f of s is equal to Laplace transform of your f of t, then we can find the final value, that is limit t tends to infinity f of t can be obtained as limit s tends to 0 s into f of s. This is what your final value theorem of Laplace transform, right? Final value theorem. So using this final value theorem, we can find the steady state error ESS equal to limit t tends to infinity e of t is equal to limit s tends to 0 s tends to 0 s into e of s. Or we can write this as, which is equal to limit s tends to 0 s into r of s by 1 plus g of s into h of s. This is what your steady state error ESS. So using the final value theorem of your Laplace transform, we can find the steady state error. So now let us see some of the static error constants. So what is the static error constants? So when a control system it is excited with a standard input signal, so when your system is applied with a standard input signal, the steady state error may be 0, or it may be constant, or it may be infinity. Sometimes you may get the steady state error as 0, sometimes it may be infinity, or it may be a constant. So this value of the steady state error, it depends on the type number and the input signal. So yesterday we have seen how to find the type number of the system, right? So these values depends on the type number and what type of input that you are applying to the system. For example, a type 0 system, so it will be having a constant steady state error when the input signal is unit step signal, right? A type 0 system will be having a constant steady state error when you apply the input as a step signal, unit step signal. For example, another example is for a type 1 system. It will be having a constant steady state error when the input signal is a ramp signal. Similarly, a type 2 system will be having a constant steady state error when the input signal is a parabolic signal, or we can say a velocity signal. So this type 2 system will have a constant steady state error when the input is parabolic signal or acceleration signal, right? So for the three cases what we have dealt with, the steady state error is associated with any one of the constants that we call it as static error constant. So we can define the static error constants as, first one, the positional error constant. Positional error constant. So it is represented as Kp. So this is the definition of your Kp, or the positional error constant. So which is equal to limit s tends to 0 g of s into h of s. G of s into h of s. So these are the standard definition of these different static error constants. So your next error constant is the velocity error constant. Velocity error constant. So it is represented as Kv, and we can define this Kv as limit s tends to 0 s into g of s into h of s. And the final one is the acceleration error constant. So this acceleration error constant, it is defined as K, it is represented as Ka. So we can represent this acceleration error constant as Ka. Understood? So Ka is equal to, K suffix small a is equal to limit s tends to 0 s square into g of s into h of s. So these are the three important static error constants, and the definitions are these ones, right? So now when we are going to find the steady state error when the input signal is unit step signal, right? So the first case is the steady state error. When the input signal is unit step signal, right? So already you know the steady state error, the definition of your steady state error, ESS is equal to limit s tends to 0 s into r of s divided by 1 plus g of s into h of s. This is what the definition of steady state error. So when your input signal is an unit step signal, then of course your r of s will be equal to 1 by s. So once you apply this r of s equal to 1 by s here in this equation, you will get that ESS is equal to limit s tends to 0 s into 1 by s divided by 1 plus g of s into h of s. So this is nothing but limit s tends to 0 1 by 1 plus g of s into h of s, or we can write this as, which is equal to 1 divided by 1 plus limit s tends to 0 g of s into h of s, right? We can write this as, which is equal to 1 by 1 plus k suffix p. This is nothing but your k suffix p. Already we have defined the static error constants kp as limit s tends to 0 g of s into h of s. Therefore this term is nothing but your k suffix p, and therefore we can write ESS is equal to 1 by 1 plus K suffix P, where K suffix P is nothing but your positional error constant. Here Kp is the positional error constant, and your Kp is nothing but limit s tends to 0 g of s into h of s. So now we are going to calculate the steady state error for different types of system. So for a type 0 system, if it is a type 0 system, what will be the steady state error for a type 0 system? So here Kp is equal to limit s tends to 0. So you are calculating the static error constant Kp g of s into h of s. Understood? So now we can write this as g is equal to limit s tends to 0 k into your g of s can be written as k into s plus z1, the first 0, into s plus z2 numerator polynomial by denominator polynomial. So this will have the standard form as s plus z1 into s plus z2 into s plus z3 etc. divided by the poles. What are the poles? S plus p1 into s plus p2 into s plus p3 etc. Understood? So now if you substitute s equal to 0 here, you will be getting it as k into, k is a constant, k into z1 into z2 into z3 divided by p1 into p2 into p3 etc. So this is nothing but a constant. Understood? Therefore the steady state error ESS is equal to 1 by 1 plus Kp. Here Kp is a constant. Therefore this 1 by 1 plus Kp is also equal to a constant. Therefore we can conclude that for a type 0 system, when the input signal is unit step, there will be a constant steady state error. If the input is a unit step signal for a type 0 system, the steady state error will be a constant steady state error. So in the second case, for a just consider a type 1 system. So we can find the static error constant for a type 1 system as, here it is a type 1 system. So for this, the value of Kp is equal to limit s tends to 0 g of s into h of s, or we can write this as, which is equal to limit s tends to 0 k into, so here you need the general form of a type 1 system, right? So we can write it as s plus z1, the numerator you are having the zeros, so s plus z2 etc. divided by s plus s into, because this is a type 1 system, therefore here you will be having S0, a pole at the origin, a single pole at the origin. That is why it is represented as s into s plus p1 into s plus p2 into s plus p3 etc. So once you substitute s equal to 0 here in this equation, the denominator will be equal to 0, and therefore the value of Kp will be equal to infinity in this case. Therefore we can calculate the steady state error. So now we can calculate the steady state error ESS as, here the value of Kp is equal to infinity, therefore we can calculate ESS is equal to 1 by 1 plus Kp, that is equal to 1 by 1 plus infinity, that is equal to 0. So we can conclude that so in system with the type number 1 and above, suppose if it is a type 2 system or type 3 system, for unit step input the value of this kp or this static error constant or the positional error constant will be equal to infinity, and therefore the steady state value will be equal to 0 for type number 1 and above systems. So that is the conclusion here. So the next case is the steady state error for a when you apply an unit ramp signal, you are just changing the input type here. So if the input is unit ramp signal, so here the steady state error ESS, as usual, it is nothing but a limit s tends to 0 s into r of s divided by 1 plus g of s into h of s. So here the input is unit ramp signal, therefore your r of s is equal to 1 by s square here, because your r of t is equal to t. So this is what your unit ramp signal for t greater than or equal to 0. Equal to 0 otherwise. Therefore its Laplace transform is 1 by s square, and therefore once you substitute this value here, you will be getting ESS is equal to limit s tends to 0 s into 1 by s square divided by 1 plus g of s into h of s. Or we can write this as which is equal to limit s tends to 0 1 by s plus s into g of s into h of s. We can cancel out this s and this s, so that we can write this as limit s tends to 0 1 by s plus s into g of s into h of s. Or we can write this as which is equal to 1 by limit s tends to 0 s into g of s into h of s. So once you apply s equal to 0 here, you will be getting this term equal to 0, and therefore the remaining term is nothing but limit s tends to 0 s into g of s into h of s. Or we can write this as which is equal to 1 by your kv, or the velocity error constant that we have already defined, right? So the velocity error constant kv equal to limit s tends to 0 s into g of s into h of s, and therefore this term is nothing but your velocity error constant, that is 1 by kv. We are obtaining this ESS equal to 1 by kv, right? Or we can write where kv, the value of kv is equal to limit s tends to 0 s into g of s into h of s, your velocity error constant. This is nothing but your velocity error constant, right? So now let us see for type 0 system what will be your steady state error. Just a see.